This is a video lesson of section 8.4, Graphing Rational Functions. A rational function, like the word ratio, as you can see right here, is a function that is fractional and of the form p of x over q of x, where p of x and q of x are polynomials, and q of x cannot equal 0. Rational functions are undefined where the denominator equals 0. And you can see that right here, and you can fill that in on your notes. And these values of x where the denominator equals 0 are where the graphs of rational functions will have breaks in discontinuity. These breaks can appear as either vertical asymptotes, you can fill that in, or as points of discontinuity, that is, a hole. So a graph can either have a vertical asymptote where the denominator equals 0, or it can have a hole. And you can see graphs that have these on pages 553 and 557, which I have pasted below. So let me scroll down here to some graphs. It's all the way at the bottom. So as you look here, you notice in these graphs that they have vertical asymptotes, which are dotted lines where the function is undefined. Notice it's x equals -1 here. Here, it's x equals -1 and x equals +1. And in both of those cases, that is where the denominator equals 0. And then in this last case, it's where x equals +3, again, because that's where the denominator equals 0. Then in this bottom case, the denominator equals 0 at -1, but notice how there's a factor of x plus 1 in the numerator as well, and that these would cancel out, and this function would simplify to become x plus 2. Well, when the factors cancel out, rather than having a vertical asymptote, you have a hole in the graph, and that's what you can see right here. When x is -1, if you plug -1 in here to the simplified function, -1 plus 2 is +1, so the hole occurs on this graph at -1, +1, which is that open circle that's part of the line x plus 2. We all know how to graph the line y equals x plus 2. That's a line that has a y-intercept of 2 and a slope value of +1. But what makes it not linear, what makes it rational, is that it is undefined at the value that makes the denominator become 0. And in this case, that value, because it cancels with an identical factor in the numerator, becomes a hole in the graph rather than a vertical asymptote like you're seeing in the examples above. Now, the one thing you'll have to know, we do use technology and graphing technology to help us here, but our graphing technology will not show you vertical asymptotes. And I require you to graph them, so you have to understand how to find them. And that's based on the values that make the denominator become 0. So let's go back up to the top and now talk about horizontal asymptotes right here. So the graph of f of x, a rational function, has at most one horizontal asymptote, and it's based on the degree of the numerator as compared to the degree of the denominator. Remember up here that f of x is defined as p of x over q of x. Well, p of x is the numerator and q of x is the denominator. So in the first bullet here, it says if the degree of the numerator, p of x, is less than the degree of the denominator, q of x, then y equals 0 is automatically a horizontal asymptote, and that's the x-axis. The second bullet says if the degree of the numerator, p of x, equals the degree of the denominator, q of x, then y equals the ratio of the leading coefficient of the numerator over the leading coefficient of the denominator. And I'll show you in an example below what that looks like. And then the third case, if the degree of the numerator, p of x, is greater than the degree of the denominator, q of x, there is no horizontal asymptote. Everybody's happy when they see that case, but the end result is you might have a slant asymptote, which we'll talk about more on Friday, but is on the back side of your notes here. So let's move down here and look at examples 1 through 4. We do use graphing technology to enter these functions on our calculator after we've found the horizontal and vertical asymptotes, found the holes, and copy a table of values from the technology. We don't look at the graph until the end because you truly need to understand how to find all those other pieces. So in number 1, f of x equals x over x plus 1. So the first thing we do is we take the denominator of x plus 1 and set it equal to 0 and solve that, and that gives us x equals negative 1. Since there is no factor of x plus 1 in the numerator, that will appear as a vertical asymptote. And you would draw a dashed vertical line at x equals negative 1 on your graph. As far as horizontal asymptotes, you will look at the degree of the numerator and denominator. So the degree of the numerator is 1. That's the power that x is raised to. That is also the degree of the denominator. The d stands for degree. Since the degree of the numerator and denominator is the same, we have case 2 for horizontal asymptotes, which says if the degree is the same, you take the ratio of the leading coefficients. The leading coefficients there are in red. They're both 1, so y equals 1 over 1, and that's y equals 1. And that's what this means when it says case 2. So I would draw a horizontal asymptote to graph this function, y equals 1. At that point, I would actually type the function into my graphing technology. Be sure to include parentheses around any numerators or denominators that are more than a single term. And then look at your table of values. And in this case, I don't have those listed out, but I can show you the graph right here. Here is x equals negative 1, y equals positive 1, and I graph a few of the points. You need to copy that table of values, and then you draw through those points using the asymptotes as guides for the branches of your graph. All right, let's go back up to 2. In number 2, the factors in the denominator, when set equal to 0, give you x equal 2 and x equals negative 3. Neither of which cancels in the numerator, so they both occur as vertical asymptotes, as you can see. And then the degree of the numerator, when you have a constant term, that degree is 0. And in the denominator, you have to understand if you took that product, it would be x squared. And so the degree of the denominator is 2. And so we have case 1, the degree of the numerator is less than the degree of the denominator, and we automatically have y equals 0 as a horizontal asymptote. So again, I would, on my graph, I'm going to slide down here, graph my vertical asymptotes at negative 3 and positive 2, and then y equals 0, which is the x-axis, and then I would make a table of values, being sure to include points on either side of my vertical asymptotes, and I would copy those points, and then I would graph the function. And you do need to make sure, like I would have had at least -5, -4, -3 is undefined, -2, -1, 0, 1, 2 is undefined, 3, and 4. So I would have at least from -5 to +4 copied from my graphing technology. All right, number 3. In number 3, the numerator actually factors, while the denominator is undefined for x equals +5. But because the factor of x minus 5 cancels, the function actually simplifies to become linear and become x plus 5, which we all know how to graph that line, a slope of 1, a y-intercept of 5. But what's key here is the fact that it's undefined at 5 from the denominator, and if we plug 5 into the simplified form, that gives us a whole at 510. And if you'd graph it, you would see that. Here is graph number 3. Right here. And I have a line that has a y-intercept of 5, a slope of 1, and then at 510, notice my open circle. That's how you deal with that. So hopefully you're starting to get the idea. The worksheet has room for you to fill in tables. I've kind of done that with number 4 here. If you look at number 4, and that's the last one I'll talk about today, the denominator is undefined where x equals 1. And it doesn't cross out with any factor of x minus 1 in the numerator, so it appears as a vertical asymptote. While the degree of the numerator is 0, the degree of the denominator would be 2. When you square that quantity, that is going to give you x squared. So we have, again, case 1, where the horizontal asymptote is y equals 0. Notice I'm giving you the start of a table where x equals 1 is undefined here, but I'm testing values on either side. It's really easy for me to test, like if I put in 0 for x, I can do that. 0 minus 1 is -1 in the denominator, squared is +1, so y becomes +4. And that's also the case when you plug in +2. 2 minus 1 is 1, squared is 1, and 4 over 1 is 4. So it's not that you can't find these values the good old-fashioned way. I'm just permitting you to use graphing technology to speed up the process. Then as far as graphing, your technology can help check your graph, but you need to be able to place your asymptotes and such so that you can graph your function. And you'll have to show those values that you copy as well. You can go ahead and look at the backside for slant asymptotes and a case like number 3 at the bottom. But that's all I'm going to cover for today. My voice is kind of raspy, so I want to save it. And I hope that helps. And I hope to be back in your class on Friday. All right. Thank you.